Hi, welcome to Unit 6.3 Kinetics. This is part 3 of 3. In the last video, in part 2, we learned that mechanisms must be reasonable, and there are two criteria for accepting a reaction mechanism as reasonable. The first is that the sum of the elementary steps must equal the overall reaction, and for that we use Hess's law. The second one, which is what we'll explore here, is that the rate law from the mechanism must match the rate law of the reaction. So let's take a look at this example here. We have mechanism 1 and mechanism 2 for this overall reaction that is shown in red. And we could prove that both of these mechanisms, when you add them up, will give you this overall reaction. So based on the first criteria, the sum of the elementary steps for both mechanisms equals the overall reaction. So now how can we tell which reaction matches the rate equation? What we're going to do is we're going to write a rate law. And let's say in another experiment, someone determined that the rate law of this reaction is raised equal to K times the concentration of NO2. So we need to figure out which mechanism will also give the same rate law. Before we go into that, let's look at the principles for determining rate laws from a mechanism. So the first principle is that the slow step is your rate determining step. So if you go back to the mechanism, you see that the first step in mechanism 1 is identified as slow, and the second step in mechanism 2 is identified as slow. And that's because the reaction is thought to it cannot be faster than the slow step. The slow step is sort of like the weakest link. It's going to slow that reaction down. And so the rate depends on that slow step, which is known as your rate determining step. The second principle is that the final rate law cannot have intermediates in the rate law. So remember, intermediates are things that are produced and consumed during the mechanism, but are not a reactant or a product. So in the overall reaction. So we don't see them in the overall reaction. We can't see them in the rate law. Now the third one might just blow your mind. You may recall that when we wrote rate laws for the initial rates method, that's when we had the table there, we emphasized that the rate orders are not equal to the coefficients. But in reaction mechanisms, they are. So the coefficients of elementary steps are your rate orders. The second thing, and I'm going to box that and have you guys box it because it's just something that we haven't been doing, so we got to emphasize that to ourselves. The fourth thing that we need to look at is that the rate of a forward reaction is going to equal to the rate of the reverse reaction when it's in equilibrium. So if ever you see something that's in equilibrium, you can set the rate laws for both the forward and reverse reactions equal to each other. And finally, remember the rate order from the mechanism must match the overall rate law order. So these are all of the principles. And I'm sorry, that should actually say rate law. So I'm going to go ahead and change that right now. Okay, so let's take a look at how we can use those principles to write a rate law from a mechanism. So here we have mechanism 1, and we want to write a rate law. And in this case, the slow step is the first step. So the first thing you want to do is identify your slow step, and here it's the first step. Once we know what the slow step is, we're going to write a rate law for it. And writing a rate law from an elementary step is quite easy. You just take rate is equal to K, and then we'll use whatever step this is. So this is step 1 to mark off our K. So we'll say this is K1 times the concentration of the reactants raised to their coefficients. Remember, for elementary steps, use the coefficients as the rate order. So in this case, we're going to get rate is equal to K1 times concentration of NO2 raised to the first power. And remember, this 1 comes from the coefficient. Now, technically, we don't need to write a 1 if the power is 1, but I'm doing it here just because I want to emphasize that it comes from the coefficient. Okay, so we got our rate law for mechanism 1. Let's go ahead and do it for mechanism 2, which is actually not going to be so easy. So in this case, the slow step is not the first step. Here, the slow step is the second step here. And again, they'll identify what's your fast and slow. So we're going to write a rate law for this. And when we do, we get rate is equal to K2 times concentration of NO3 times concentration of CO. So let's just break that down for a moment. Remember, K is the rate constant. And here, because the slow step is step 2, we use just a subscript 2 to mark off that this is K2 for step 2. Now we have the concentrations of the reactants. And the two reactants in the slope step mechanism 2 are NO3 and CO. And they both have a coefficient of 1, so the rate orders are going to be 1. Okay, one thing to note here in this rate law is that we have an intermediate. NO3 is an intermediate, and according to our principle, we cannot have an intermediate there. So we have to find a way to get rid of it. And usually the way we get rid of it is we look for a reaction that's in equilibrium, because we can use this idea of rate of forward equals to rate of the reverse. And if we can set these two equal to one another, we can use them to isolate and solve for the concentration of our intermediate, so the concentration of NO3. Then we can go ahead and plug that into this rate law. And once we have it plugged in, we can get rid of that intermediate. So this is all about math at this point. So let's see what I mean. We're going to set the rate of the forward equal to the rate of the reverse. So for the forward reaction, it's going to be K1, 1 just being the first step, times concentration of NO2 times concentration of NO2. We'll simplify that in a moment. The reverse reaction, the NO3 and NO are the reactants. So it's going to be K minus 1, minus just implying its first step, but it's the reverse of the first step, times concentration of NO3 times concentration of NO. And again, we're using these because these are the reactants of the reverse reaction. So let's go ahead and simplify this side. We get K1 times concentration of NO2 squared as equal to K to the negative 1 times concentration of NO3 times concentration of NO. Notice we have concentration of NO3 here, so now we're just going to use inverse operations to isolate concentration of NO3. To do that, we're going to divide both sides by K minus 1 times NO, and that makes these two cancel out, leaving us with the concentration of NO3 is equal to whatever on this left side here, which is K1 times concentration of NO2 squared divided by K minus 1 times concentration of NO. Now that we have that value, we're going to go ahead and plug that in to our rate law. Once we have that plugged in, it will look something like this. So all I did was wherever I had the NO3, I just plugged in all of this stuff here, and I got this rate expression. If you need to pause the video to sort of see what it looks like or how I got it, or do it on your own on a separate piece of paper, I would recommend you do that. Now I'm going to simplify this by combining all of my K's. So I'm going to use my understandings of fractions, and when you multiply fractions, what happens. So I'm going to combine all the K's, and I get K2 times K1 divided by K minus 1. And then I'm going to also combine my concentrations. So I get NO times NO2 squared all over CO. And that's the rate law that I get for mechanism 2. So again, if you need to try this, I would pause the video now and on a separate sheet of paper, see if you can try this. All right, so before we go into sort of proving which mechanism matches the rate law, let's just take a moment, see if you can do it. So for this CFU, you are given this overall reaction here, and you're going to prove whether or not this mechanism, you're going to use this accepted mechanism, meaning that they've already proven it works. So you're going to use this accepted mechanism to write a rate law for the reaction. So we're just practicing how do you write a rate law from a mechanism. Pause the video now, and when you press play again, the answer will be revealed. Okay, so the slow step is the second step, and the rate law for that is going to be K2 times concentration of O times concentration of O3. Remember, the 2 here just means it comes from the second step. If it came from the first step, this would be a 1. If it came from a third step, this would be a 3. All right, remember we cannot have an intermediate in there, so the intermediate here is O, so we need to get rid of it. We're going to use the understanding that the rate of the forward equals the rate of the reverse for that first reaction there. When I do that, I'm going to do what I need to do to solve for O, which is the intermediate I'm trying to get rid of, and this is my work for that. Once I have what O is equal to, I'm going to go ahead and plug that into my rate law. And I get something like this. Then I'm going to combine my K's and my concentrations, and I get something that looks like this. So this is the rate law for CFU4. If you're confused, I would take a look at this work and see if you can try it on your own. All right. Now, let's go back to what we started off with, which is the reaction from the beginning, and we were trying to figure out which mechanism is acceptable. Okay, and we were told that the rate law for the reaction above is rate is equal to K times concentration of NO2. And we found, we had already found previously what the rate laws are for mechanism 1 and mechanism 2. So if you need to go back into your notes, find those. Okay, so based on those, the rate laws that you determined for mechanism 1 and mechanism 2, which mechanism is acceptable? Pause the video now, and when you press play again, the answer will be revealed. Great, the answer is mechanism 1. So if you remember, the rate law for mechanism 1 is rate is equal to K1 times concentration of NO2. That matches what we see here. It's first order with respect to NO2. And then for mechanism 2, the rate law is equal to all these Ks times concentration of NO times concentration of NO2 squared all over CO. So this is a much more complicated rate law. All right, I want you guys to do that from the beginning to the end with this, with these mechanisms now. So we're told that the rate law of this reaction is equal to K times concentration of NO2 squared times concentration of H2 squared. This is the accepted rate law. You need to figure out which mechanism is accepted using the two criteria. First of all, do they add up to this overall reaction? And do the rate laws that you need to determine for mechanism 1, 2, and 3, does it match this reaction? There's a lot of work here, so I would pause the video now. And when you press play again, I will show you the answers. So take your time on this because this is a super important question. Okay, so here's the work here. Mechanism 1, mechanism 2, mechanism 3, there are their rate laws. And the mechanism that matches that rate law is mechanism 3. All right, so if you're not sure how to do this, come into class with questions. That's it for this video. I will do some reflection and summarizing. Have a quality day.